everybody. This is actually our last Friday control seminar of the year, since I think every religion has a holiday next weekend. And I'd like to thank my, if you guys are coming all year, I'd like to thank my organizer down there, who's really been great, especially at hooking up the electronics. And he's going to introduce them.
Yeah, thanks, Dean.
I'm just going to turn off lights. There we go.
Oh, yeah, this is better. So as you see, I'm good with electronics, not for with electric switches. So I have the pleasure here having Nima. So Nima, he's coming from the robotics department, as we all know. Plenty of affiliations across the College of Engineering, which is great. So yeah, Nima, we hung out for quite a while now, so it's a pleasure having you here. I look forward to all the experiments and all the work that you are going to present. He's coming from a PhD at MIT, which we didn't overlap, I think.
Just a tiny bit, yeah.
For a tiny bit before, yeah, he did his bachelor's at Maryland University. He has multiple awards, which surprisingly you didn't list any in your bio. This is an IROS best paper or a LICRA best paper.
Yeah.
RSS
best, yeah. Should I put them in there?
Huh?
Should I do it? Should I put them in? Probably. Okay, I'll do that. Okay.
Yeah, I was expecting to see those. NSF Career Award, so plenty of intellectual power. So yeah, we look forward to the talk. Yeah.
Thank you so much for the awesome introduction. Is my audio okay? Coming through? Yeah. Thank you for the very kind introduction, and I'm excited to show you guys the progress we've been making on dexterous manipulation from vision and touch. Before getting started, obviously none of this would be possible without my wonderful research group who are viewed here. Anything that you like is theirs. Anything you don't like is my fault. And our wonderful sponsors, without whom, again, this would not be possible. So what is the hope or the dream for our research program? This is kind of what we want. We want dexterous systems like Wally capable of autonomously navigating their environments, interacting with their environments, playing with things, interacting with things, learning from them, learning their articulations, their physical properties, mass, friction, even what to do with them. I just love this video for its childlike curiosity. My hope is one day we will have systems capable of this kind of curiosity. All right, and so what do I think are the key ingredients to getting the level of capabilities that Wally has? I think these are sort of the three key ingredients: having 3D or 4D physical representations, thinking about object-centric representations, and having multimodal feedback. So I'm particularly interested in vision and touch. There's no reason why audio, language, and other modalities could not be involved. And so given that this is what I think are the key ingredients, this is what a typical robotic setup looks like in our lab. We have sort of this visual image from the scene. The robot is grasping an object. It has access to tactile feedback coming from the fingers. It has access to force torque feedback coming from the wrist, and it has an object in the grasp. It's interested in doing something useful. So can I apply forces? Can I flip things? Can I push things? Can I just basically physically forcefully interact with the environment? For us to be able to realize these capabilities, of course, in addition to vision, we need to understand touch. We need to be able to build these multimodal object-centric representations. And once we have these, we need to be able to plan through contacts. We have to do contact-aware planning. And so with these sort of three key ideas in mind, these are the pillars of the research program. And today, my hope is to convince you of two things. One is that tactile sensing is rapidly becoming a technology, and it's super easy to use. So in case you're interested in taking on this technology, do it, super easy. And I also want to convince you that model-based methods are still powerful despite all the hype you're hearing from these massive scale pixel to action stuff. Okay, so to convince you of the first item, let's think about understanding touch. We're going to talk a little bit about the importance of touch, thinking about tactile perception and controls, thinking a little bit about generalizable tactile representations, and I'll touch on some of the tactile hardware we've developed. Now, to illustrate the importance of touch, I really like this visual. This is the creation of Adam by Michelangelo. And as with great art, everyone has their own interpretation. To me, what is interesting here is the centrality of touch. In fact, Adam is reaching out in order to touch God. Touching divinity is a very common theme in Abrahamic religions. Other Abrahamic religions argue that the soul is past the human body to touch the back of the neck. Now, If you don't like theology or history, touch was actually much more central to your cortex than your visual apparatus is. Touch was evolved much earlier. It's much more central to your cognition. If you don't care about biology, you don't care about history or theology, there are very practical applications. You may use touch to detect slip. You may care about grasp force modulation, something that I'm doing with my coffee so I don't spill it. Shear estimation, so for example, when you're pulling on something like rope. Object localization when you're reaching into your bag of groceries, or even palpitation, which is a common procedure happening in medicine. For example, detecting lumps and cancer and so on. So hopefully I've convinced you that touch is worth studying. This is the kind of touch that we study in my group. This is called vision-based tactile sensing. So on the left-hand side, this is the sensor. This is one example of the sensors that I'll show you. It's an inflatable membrane. There's a camera that perceives this membrane. And here we're transducing the deformations made in that membrane into a visual modality. This is a point cloud as collected by a camera that is located right here. So there's a camera here. It's perceiving that membrane, and this is the visual perception of that camera. Again, we're transducing a mechanical deformation into a visual modality, hence why we call it a vision-based tactile sensor. And so the goal here is, given that modality, how do I produce behavior like this? How do I go from sensory motor to skills? Now, fortunately, this is a control seminar, so this should be pretty kind of standard. Assuming we have access to actions, these are the end effector motions, assuming that we have access to force torque readings of the wrist, assuming we have access to the tactile perception that I showed you, and some notion of an object, here's what we're trying to do. We're trying to minimize our discrepancy with respect to some goal state. Here, X represents things that we want about the object. For example, driving as opposed to a certain configuration, applying a certain amount of force to the environment, something that's very object-centric. And here, our actions, again, are end effector motions. We don't want to have very jittery motion. We want to have relatively smooth motion, hopefully. Now, obviously, this without any sort of constraints is worthless. The kind of constraints that we think about are tactile or object dynamics. So, for example, given the current tactile measurements, the forces that I feel, and the actions that I'm about to take on the particular object, what will be the future evolution of my tactile precepts, my forces that I'm going to be applying? This is called like a dynamics model. These days, they'll call it a world model or whatever, dynamics. In addition to that, we need an observation model. This will map tactile precepts to these object-centric features. So X, I said, contains something like configurations. Here, Q is configuration, for example. So I want to infer, where is the object in my grasp? And we favor this type of representation because it offers sort of two very nice features, this modular design. One is that it's quite flexible in task specification. It's quite amenable to different kinds of cost functions that you can come up with. And it has, we've noticed in experimentation, yielded better generalization by learning these powerful tactile world models. So I'm going to show you kind of how this architecture looks. This is typically what you would do when you're doing model predictive controls. You have a model predictive controller. You have a perceived notion of the world, that is the sensor membrane state. You can forward predict how this membrane state will evolve as a function of the actions you choose. And then you can convert those predictions into observations about the object that you're manipulating. You can look at where that is. Is it good? Is it bad? You can modify your actions until you minimize the discrepancy with what you want. Right? It's pretty traditional MPC. With that in mind, okay, so how do the membrane dynamics and the observation models look? That's sort of the key two parts here. This is kind of a typical perception stack. You kind of read this from left to right. We start with the deformed depth maps. These are the tactile signatures. We can compare them to undeformed tactile signatures and extract what are tactile imprints. This is basically what the imprint of the object in the grasp. We can use a notion of the object and external environment to infer something about the object pose and the forces transmitted to the environment. It's sort of like a perception stack. And this works remarkably well. I would even argue this is almost a technology. On the left-hand side is a robot. We've just handed it a marker. And what we're asking is to just try to predict what is the orientation of this marker. And here you'll see like a little cylinder kind of trying to align itself with the marker. That is our internal belief. On the right-hand side, we can get even a little bit fancier, which is to say, here's a spatula. Can you simultaneously infer, given what you know about where the table is, what is the pose and where is the contact being made? So every time you see like a little red light up, that is where it believes the table, the contact with the table is being made, and that's the in-hand pose. Okay, and this is pretty nice. This runs at about 10 Hertz. It works remarkably well for rigid objects. It's good at extrinsic contacts. It's a relatively well-established baseline at this point. You can use our software libraries. You can make up your own. But I would say this is like a pretty mature capability at this point. Now that you can do perception, you can also think about dynamics. So our dynamics typically look something like this. We start with the raw tactile feedback, the force that you feel at the wrist, and the proprioception of the robot. This is R sub t. This is your notion of the object. Usually we use point clouds that are embedded. We take our robot actions and we try to predict future evolutions of your tactile representation, your forces, and your proprioception. There's a little subtlety here of why we predict proprioception in the sense that our robots run an impedance control. An impedance control, you have to kind of a priori know the gains. Because we don't a priori know the gains, this is effectively learning impedance control alongside our model. Now that you have your tactile dynamics, you have your perception capabilities, what can you do? Here's our robot. It's performing something called we call in-hand pivoting. This is completely blind. This is just using tactile feedback, but we're going to hand it an object. It is in the incorrect orientation. It has to be aligned with the green, and everything else is autonomous. This is just model predictive control. It's going to plan for a sequence of actions such that it makes contact with the environment, does a little grasp adjustment, and lifts up. Let go again. And basically, you can hand it anything that kind of looks like a spatula-looking shape, and it will do this for you over and over and over again quite reliably. You can do other tasks. So this is a drawing task where the goal here is to draw the longest line along this salmon sort of a representation. If you are not careful, these sensors are quite weak towards shear, and so the marker is slowly shearing out of the grasp as it's drawing. But here, the robot is continuously adjusting its grasp to keep the marker about as vertical as it can before it gives up. At some point, it says, I don't think I can keep it vertical anymore, it will give up. If you use some sort of traditional control techniques, about the best you can do is here. It's a surprisingly difficult task, even though it looks kind of simple. You can get even fancier. Here's dense insertion. Again, in this task, the robot is going to grab an object, and the objective is to shove it into this little area here. The problem is it's too small, so it has to make some room. It has an understanding that these objects here are able to move. There is some amount of compliance in the environment. So it's going to try to basically push against them, create a hole that is big enough, and then jam the object in. Again, the red here, this is the understanding of where the external contact is being made. The green is a perception of where these objects are, mostly driven by touch. And the pink and here orange, that is again in-hand pose estimation.
What is this cylinder, red cylinder that appears? What kind of inference outcome is that?
That's where it thinks the contact is with the environment. Yeah. And these other colors are just pose estimation results. And then you can get even fancier. So what you saw so far, the environment was not that interesting. Here the goal is to balance an object on a corner, given an object you're grasping. So here, I want to use this object that I'm grasping to balance this object on a corner. And so what's challenging here is you have to worry about the frictional interaction between your grasp and this object, and this object, and then this object in the environment. It's a massively underactuated and pretty complicated system. You're dealing with unilateral frictional constraints and hybridness, yet we are able to do this shockingly well for pretty much any polygonal object you hand to us.
Just one
Yeah.
question, like, what are you observing here? Take back plus the April tags?
The April tags are just for tracking. It just knows from the very beginning just where the objects are approximately, and then it closes its eyes. So it has no visual feedback.
It's motion, there's no feedback.
There's no visual feedback at all. It's purely touch. But it can infer the state of the other object given sort of the tactile feedback that it has. Yeah.
Good question. Do you know the mass of the objects or you know
We just, I don't know if we know exactly the mass, we just approximate to be the center of mass, and then online it just infers some approximate value.
Important force estimation.
We don't estimate contact force directly, we just require it to be within the bounds of sticking.
Oh.
Yeah, so that happens to have some nice properties.
So following up on that, you had previously presented a mathematical framework where that was built on a dynamic model, discrete time dynamic model, but dynamic model nonetheless. Can you get into just what are the state variables associated with that dynamic model, and how, if that dynamic model is characterizing the evolution of the object that you're interacting with, and yet you don't know the inertial properties of that object, how
That's a
How's
great
it work?
question. That's a really great question. So there's a few details there. The first detail is that the state from the perception of our learned models is the tactile membrane. Then there is a notion of the object itself from the tactile membrane that is inferred. That's like composed. We just assume the objects are rigid. And so that's kind of good enough there. Under the quasi-dynamic assumption and quasi-static assumption, these are what we call form closures or force closures that we can produce. And there, these particular closures are robust to any external perturbation, any force you apply externally. So as long as you satisfy the constraints for a force closure, actually the mass does never matters.
I see.
But it's only true for the non-dynamic case. So if this was a dynamic manipulation, this would no longer hold. We would have to know inertia.
So presumably, because this is happening in kind of a
Slow enough, exactly.
way, yeah.
That's the magic sauce. It has to happen slow enough. And honestly, like in about 10 years of like doing manipulation research, I've yet to like make something move fast enough that inertia plays a big role. I started my PhD thinking it was important, and then it turns out most manipulation skills are too slow for dynamics to really matter. Yeah.
Does it go with sliding friction?
There I have, not here, but other demonstrations where we can do sliding. So you can choose what you want. You can have it, you can have this one slide, you can have this one slide, you can choose what you want and it can realize it within reason. Yeah.
To understand a bit better, are you learning a model per object, or is there just one membrane model? and
There's
it's
one
like
membrane model for all things.
all these
Yeah.
different objects?
It'd be super painful to learn one by one. No, it's not necessary. Just one usually is good enough. Great. So you might see this and be like, hey, this looks like you've made a lot of progress on tactile dexterity. Is the problem solved? And no, there's actually kind of some major issues with what you've seen so far. And they are to do with the observation model and the tactile dynamics models. These, as a kind of a high level view, there's effects of geometric aliasing, something that I'll point to shortly. You have to worry about generalization across sensors. All I've shown you is one sensor, right? I haven't shown you other types of tactile sensors. You've just seen the soft bubbles. There are other artifacts called tactile shadows, and then there's the question of generalization across embodiment, which I won't get into today. So geometric aliasing is kind of an interesting artifact. So suppose that I give you the robot, that thing over there is a robot, and it's holding this, this cylindrical object over here near the top. So this is state one, X1 is the perception from touch, and I command it to do a 90-degree rotation. So this U is a command that says, go from S1 to S3 by just rotating your hand 90 degrees and moving slightly up, right? You end up getting X3. So you can see the top of the cylinder kind of showing there, right? This thing up here, that's the top of the cylinder. Now, here is the same kind of a situation where the robot is grasping the object a little bit further down, S2, and I command the same action. So even though X2 looks just like X1, X4 doesn't look like X3. So from a purely sort of a perceptual feedback, you cannot tell the difference between which, you can't tell which outcome will be happening without that additional contextual cue. This is something that we call geometric aliasing. You may say, so why do you care about such a thing? When you're learning representations that are encoder-decoder, this has a very big impact. It results in something called mode collapse. So given these states that you start in, here S1 and S2, taking the same action U should result in two different states. However, because the perceptual feedback is sort of ambiguous here, you're going to get a mode collapse in the latent space. This is a bad thing to do. So our attempt to address this was to propose a decoder-only architecture. And so the top figure you read from left to right, and these figures you read right to left. You learn directly in the latent space and you decode into the observation space. You don't go the other way. You don't encode, then decode. You directly just decode always. And so we instantiate a bunch of latent vectors. And from these latent vectors, we can decode. These are okay to map to the same locations in observation space because they will be separated out again because of the actions we take. How do you separate them out in action space? By learning action models. So this is just purely a decoder architecture. I'm sampling some random vector from a unit, a normal distribution mu1, sigma 1. I decode it, I get x1. And what I'm going to do is condition on the actions I take, here a sub 1, I'm going to try to predict future outcomes, okay? And here again, I'm going to also learn A and B. So I'm learning psi, I'm learning A, and I'm learning B. And by performing this sort of a decoder-only architecture, you can significantly mitigate the issues of geometric aliasing. To demonstrate this idea, and fortunately this is a controls crowd, this is our take on the cart pole problem. This we call the tactile cart pole. The idea is I have a cart, I'm gonna yank it, and the robot is trying to grasp the pole. The objective here is for the robot to try to make the pole go vertical whilst I'm adversarially trying to pull the cart out of the way. If you turn off our anti-aliasing controller, you'll drop it almost instantly, about 2 pivots, and it will fall right out. With our anti-aliasing controllers on, you can keep this up for about 5 minutes or so. This cart pole idea was kind of a neat idea because currently in our domain of manipulation, there are no baselines or benchmarks for evaluating the quality or fidelity of tactile controllers. And this will go on for a while. So this is a bit more in the context of controls. This is a purely perceptual task done with object handover. Again, there's a significant amount of aliasing, but the robot is able to, just by pulling against the human, infer roughly what the pose of the object is. And from pulling against the human is able to make the object horizontal. Every time you see a check mark, the robot is confident and correct in making the object horizontal by adversarially pulling against the human. Now, with geometric aliasing largely solved, there's a question of generalization across sensors. And so, again, suppose I spend a bunch of time developing these perception capabilities, everything I've talked about so far, and then someone comes along and gives you a new sensor, right? Maybe I give you a gel stem, a digit, or whatever else. And then the question is, how can I, without recreating any of my algorithms, achieve the same perception capabilities? I don't want to do everything that I just did once again. That would suck. And so the question is, like, given that I showed you this capability over here on the left-hand side, how do I realize the same capability on a tactile sensor that looks wildly different on the right-hand side? And so there's a few different ways you can go about doing this. I'm going to talk about 2. The first approach is something we call touch-to-touch. And so the idea is that suppose I give you these new tactile sensors over here that you've never seen before, these signatures you've never seen before. You're going to hallucinate what these signatures would have looked like had you collected them from a sensor that you had access to. Then you're going to run your perception capabilities on the thing that you know how to run your perception capabilities on. And you're going to behave as though they are ground truth. And you're going to keep doing this in a loop. The way that you train such a model is you take paired data. So here I have data collected from the same object in the same grasp, but with 2 different sensors. So this is sensor 1, this is sensor 2. And you can see just by visually looking at these signatures that there's some similarity, right? You can see sort of like a little Y shape here, there's another Y shape here. And what we're doing is basically training a model, in this particular case, because diffusion models are cool, we're training a model that will take one sensor in, here the gel slims, and try to predict how this signature would look like if I were to collect it from the other sensor. Then what I do is, given that I have access to the reconstruction as though the other sensor, I'm going to run my perception stack on it and act as though that's ground truth. And so here's that task in action. So here it has no idea how to do pose estimation for the gel stems, but it does know how to do pose estimation for the soft bubbles. And ta-da, it can stack stuff. Now, you might complain and say, well, this looks like it's kind of very specific to these two tactile sensors. I've learned a model to map directly from one to the other. How do I learn more flexible representations? Another idea then to address this limitation is to do something called contrastive learning. So this one we call CTTP, and given the same sort of data set, what you can do is say, okay, signatures that have are basically positive pairs, I'm going to map into the same space and latent space. And signatures that have negative pairs, so this one and this one, I'm going to push away from each other. This is kind of what you do with clip models. So if you've ever used a clip model for vision language, this is exactly how that thing works too. It's a pretty well-established pipeline in machine learning. Once I have this really well-formed latent space where similar signatures are mapped to the same space and different ones apart from each other, I learn all of my perception capabilities in this latent space. Then I don't care which sensor produced a particular signature, I'm just going to go with it. And so here, for example, the MLP that I'm showing here is doing in-hand pose estimation and object classification. So the demonstration here is all of these shapes have different geometries, and what we're doing is we're trying to infer which shape is it and what is its pose. And if you can infer correctly, you should be able to insert it into the right hole correctly. This robot doesn't know what to do with the gel stems or the soft bubbles. It's just seen the MLP trained on latent space. Very nice. So now we have techniques available to us to be able to do generalization across different tactile representations. We can address some of the geometric aliasing issues. There's one other issue I want to touch on, which is something we call tactile shadows. And these are sort of artifacts in touch. As you might have noticed earlier on, I showed you that these sensors produce signatures that are due to deformations, right? I apply some object geometry into the membrane deforms in some shape. And the deformation is not all due to the contact. There's some artificial sort of deformations over here that kind of obfuscate the object pose estimation, right? It's like I want the T shape. My ideal thing would be to see the T shape. I don't get to see the T shape. I get to see sort of a blob with a T shape sort of showing up approximately. So how do I get rid of the noise? How do I just extract the T shape indirectly? And so the way that we do this is something called tactile neural de-rendering. The idea is, given the tactile signature, what I'm going to do is I'm just going to erase the tactile sensor completely. I'm going to render the image as though it was collected from a depth camera. And so the way that we do this, again, is with diffusion models. We're going to take this initial signature, we're going to diffuse through it and re-render it as though you had it from a depth camera. To train such a model, we take a very modest data set of sort of features that we engineer into the environment. We have the robot kind of go in and touch them. And because we have ground truth geometry, we know what those renders should look like. We also put together a very, I'd call it jank simulation environment where we can render also tactile signatures as though they were viewed by the tactile sensor. Again, it's a very incredibly coarse sort of simulator, and combine the data set from the real and the sim and train this, again, big diffusion model. And what's really interesting here is, and maybe what I want to try to highlight here is, even though the simulator was pretty terrible, having the addition of maybe 24K synthetic data significantly improves your capabilities in terms of estimating object pose in such a way that if you just use real world data, you'd be 2x worse. And so any synthetic data you can get your hands on that kind of looks like the task does an enormous amount of benefit in terms of machine learning. Good. And maybe the last thing that I'll touch on in terms of tactile sensing is our foray into making them. So here is the Jocelyn 4.0 from our group. This is a American dime, I believe, which is about yay big. That's the Michigan M right next to it. So you can imagine this thing is teeny tiny, right? Imagine I take this and just push it into the sensor. This is what you see. So it's an incredibly high fidelity, sort of a high resolution feedback of the contact interaction You can easily see your fingerprints. You can see human hair if you push into it. These are extremely sensitive. We can estimate also for, well, they're super cheap too. You can make one of these for about $50. They're designed to be reproducible, reconfigurable into different form factors, and we're also providing an out-of-the-box library that you can use. So if you're interested, you can do depth estimation, you can do object pose estimation out of the box, and it's pretty useful in case you are doing robotics, you're interested in tactile sensing. This is available to you. Now you might say, oh my goodness, this is so much work. I don't want to make a tactile sensor. Is there an easier solution? Maybe you have that thought going in your head. And turns out for some applications there is. And that easier solution is audio. So far we've thought a lot about vision-based tactile sensing. I'm going to show you a version of audio as touch. In this particular problem, we have one finger that has a contact mic on it, and another finger that has a speaker. Basically, one finger is yelling and the other one is listening. And you're going to grasp an object, and you can tell things about what is the object, what is its material properties, whether it's hollow, whether it's full, whether it's making contact with the environment, all from these signatures in audio. And so the applications would be when you have heavy visual occlusion, when you have various surface types, when you have sort of like near contacts that are hard to tell from vision. So if you just look at that, it's pretty hard to tell from vision whether you're in contact or not. Audio will instantly kind of figure it out for you. And so the secret sauce is this. You apply sort of chirp signals. These are sweeping sine waves. So you basically have a distribution of different frequencies in sine. You play it through your speaker. You listen to the signature and you turn it into something called a Mel spectrogram. Why a Mel spectrogram? There are really, really, really powerful VITs, vision transformer models that have been trained on internet scale spectrograms. And so you have access to these very powerful backbone neural networks. What then you can do is take your visual feedback, your auditory feedback, and do cross attention between them. So here, fusion is just a big transformer. It's going to take the two modalities. And here in this particular problem, we're doing contact probability maps. So this just says within the field of view, where do you think the object you're grasping is making contact with the environment? So it's just assigning a probability to every pixel in your view of the contact location between the grasped object and the environment. And so you can show for a variety of different sort of objects in the environments, like pears and Pringle boxes and I don't know, cups and whatever. I can bang them into the environment, drag them around, and I can make some inferences about where the contact is in the environment. Now you might say, oh, this is pretty cool. Audio is interesting. It's a really useful perception capability, right? What if you could do actuation with audio? So if you make the speakers high frequency enough and loud enough, you can make the object move. So in this particular task, we basically want to reconfigure the grasp object. And so by just playing audio, we're making the object move in the grasp. And we have some very simple models and some closed-loop controls. It's a super simple closed-loop control. It's like a PI controller, nothing too fancy. You can basically say, hey, I want you to go from some initial configuration in the grasp to some new configuration in the grasp. And by stop-start playing audio and reconfiguring the hand, you can make the object kind of walk. This was just accepted to RSS. Yay. So yeah, there's a lot you can do with touch. Touch is super cool. Audio is cool. Vision-based tactile sensing is cool. I would say perception is really getting there. We have really powerful capabilities for in-hand object pose estimation. We're great at shear estimation. Extrinsic contact is getting there. The controls problems, I would say, rigid object manipulation is getting there, really. We're making really good progress. If you're interested, deformable object manipulation from touch is a wide open field. Like basically, there's almost no results in the space that are convincing. And in terms of hardware, I'd say we're very good. You can use our hardware. You can use other Digit 360, GelSlib, softball, whatever you want. There's a ton of hardware. I don't think hardware is our limitation. I think tactile sensing hardware is pretty mature. Not that we should necessarily stop doing research there, but pretty mature. These are the two hard problems in this domain. Cool. So I hope I've convinced you that tactile sensing is rapidly becoming a technology. It's around the corner, and our controls capabilities are getting better. Now I want to convince you that model-based methods are still cool and powerful. And maybe you don't need that much convincing, but we'll get there. So what I'm interested in is, can you learn representations that will enable you to infer things about the object, especially when it deforms under massive visual occlusion? So here I only get to have this single view. Can you make an inference about the deformation of the sponge that you're grasping where it's making contact? Can you make inferences about the chain despite heavy visual occlusion from vision and touch? And you may say, okay, what is the application for this? It's primarily in tool use. So here's a number of examples of tool use. And there's really two reasons why we as humans use tools. One is for morphological modification. So if I wanted to turn the screw, I can never generate enough torque with my fingers. I grasp like a wrench or, sorry, screwdriver, and suddenly my hand is functionally changed, right? It went from a deformable 5-finger thing to a single rigid metal thing, right? I can generate a lot more torque. Another popular reason why we as humans use tools is to protect either ourselves. So I don't want to scrape with my fingernails, that sucks. Use a scraper, or I don't want to contaminate the food that I'm producing. So I should best use tools. And so what are some of the characteristics of tool use? It's really a dance of geometry and force transmission. So geometry means there's a collection of points. These points are in 3D. They belong to the tool. And these points can move, right? They can move with respect to each other, and they can move as a collective, right? This is the deformable objects sort of paradigm. Rigid objects are a subset of deformable objects where these points are constrained to move together, but not with respect to each other. And this sweet spot in the middle, which is called compliant objects. These are objects under which these points are allowed to move with respect to each other, but under constraints. These are usually Hookean laws. And I really like this set because they allow you to produce really interesting contact formations, force transmissions, deformations. And this is really what I mean by the dance between geometry and force. You can really use compliant objects to apply very interesting force profiles. So how do we think about this problem? Well, we really care about object geometry, P sub t. We really care about the forces transmitted to the environment, that's F sub t. We really care about the robot actions, that's A sub t. We really care about the boundary conditions, so where are you making contact, how are you making contact? And we're interested in predicting the evolution of these points and these forces as a function of time. And I'm very deliberately writing this as an implicit function because you have to do these all at the same time. You cannot resolve forces, then locations, they have to be done at the same time. And what makes this problem interesting is that this is a massively nonlinear and discontinuous problem. It's very high dimensional. And we want to do this, we want to solve these kinds of systems in heavy visual occlusions and with only partial local tactile feedback in a variety of environments. So how do we get there? Well, let's first think about what we have access to. Here's a visual scene. My robot has a spatula in hand, it's trying to serve some peas. And what I get to see is a partial view of my spatula. So P hat T just means I get to perceive a subset of the points P, and I get to feel the forces at my wrist. What I'm interested in is solving this equation to infer what is the full object geometry, P sub T, and the boundary conditions. And I also want to predict conditions on the actions that I have access to, how these points will evolve in time, how the forces will evolve in time. And so how do we do this? We are really, well, I'll just skip over why FEM and why particle models suck. But anyway, that's a story for later. We are really inspired by progress in graphics and signed distance fields. So these are like a foundational tool in computer graphics. Here's what a signed distance field is. This is a Stanford bunny. That red blue thing is a cross section of the Stanford bunny, and a signed distance field just says for every query in 3D space, where is the closest point on the surface of the object? If you're on the outside, it will be positive, and if you're on the inside, it'll be negative. And people have shown that you can take these representations and learn internet scale representations of ShapeNet, for example. And so taking a look at what I wrote down earlier, simplifying a little bit, so ignore forces, deformations, ignore actions, you're just left with this sort of a G of P T at 0. And if you notice this, if I replace P with a query in 3D space, I suddenly have a signed distance field. And so really what I wrote down is a particular solution to a signed distance field problem or a boundary value problem. And so what we want to do is work our way back from this to this. So we want to include forces. We want to make this dynamic. We want to add in actions. We want to add in boundary conditions. And this one slide is all you need. The way that we do it is, suppose I give you this object over here, and it's the deformed state over here. This is the SDF for when I haven't done anything to it yet. So I'm just taking a slice of it. I haven't deformed it. Nothing has changed. Cool. Suppose that I deform it. Now this is a new sign distance field. What I'm interested in doing is learning a vector field that if I take this vector field and add it to this one, I should get that. That's all it is. If I can learn this vector field and add it to my deformed shape and recover my nominal shape, I am good. And what I want to do is I want to make this deformation vector field conditioned on the particular force properties, the robot action, and the boundary conditions. If I can do that, I have solved my boundary value problem. It's super great. Now we're solving PDEs. Our particular instantiation of this problem, and there's now even newer versions of this, is, okay, suppose that I give the scene, I give you my configurations of my robot, my forces, and C sub t is something we're going to learn. I can produce something called a force code together with my object code. I can have a deformation module. This is the vector field representation. Adding it to the particular deformed object geometry, I'm going to recover my nominal geometry, run it through an SDF representation, and from that do reconstruction. This is stamp a bunny. This is static, so I can add in action conditioning, and I can figure out future instantiations of this SDF as a function of time. How do we learn such representations? You can basically have a robot collect play data. So here we have a robot grabbing different kinds of spatulas, jamming it into the environment, having fun. You can also have sort of chains and whatnot. And you train your representation on this data, and you can run it. So here's some inference results. So on the left-hand side is the raw RGB feedback. On the right-hand side is what the depth measurements look like. And magenta is our belief of where the spatula is in 3D space and the contact it's making. So you'll notice that despite heavy visual occlusion from the P's that it's trying to serve over there, and those are fake P's, you'll see that even though the spatula sort of disappears behind them, we can still fully recover its geometry. We can infer where it made contact, how much force it was applying, and so on, which is really cool. There we go. We can also do this for chains. So on the left-hand side, bottom left-hand side, that is a raw view, so you don't get to see where the chain is making contact with the environment. Magenta is the model's belief over where the chain is. Again, it's able to do full 3D reconstruction from vision and touch. And I think the most interesting thing here is how it actually performs state estimation. It's something that I think is quite non-traditional. So how do we do it? Given a partial view and wrench feedback. So here's my object, it's deformed. This is the camera's field of view. This is what I get to perceive. And so given this partial view of my object, my reaction wrench and my robot configuration, how do I infer the full geometry of my object? The process is something called inference via optimization. What we do is we basically freeze our entire neural network, and the only free variable in this network will be the C sub t. Everything else is completely frozen. And so by doing gradient descent on the loss function we use to train our model, we can basically do inference over C sub t to find the one that best matches the visual observations over here. And so this is our initial starting belief. As you run this gradient descent on C sub t, it will slowly converge to the ground truth. And this is some of the older version that's running at 2 Hertz. The newer versions are running at about 10 Hertz, which is super cool. And it's quite unorthodox. Usually when people talk about inference and machine learning, they're doing forward passes of the network. In our case, we actually do inverse passes. Something that's a powerful side effect of this type of representation learning is that you get dense correspondences without supervision. So here, what I'm doing is I'm painting my spatula, all these different rainbow colors, and I'm showing you where these points move as I deform it, right? So you can see, okay, as I begin to deform this object, the red moves along, it's good. And there was no supervision required to produce this correspondence across these deformations. Now, an astute observer might say, I don't believe you. And you might not believe me. You shouldn't believe me. If you look over here, it looks like the correspondence sort of breaks down a little bit, right? I'll zoom in a little bit. So up until like folding the spatula about 90 degrees, it looks fine, right? It's pretty good. Once you really try to fold it in half, this is when you begin to have some trouble. The correspondence sort of breaks down. And this is because the neural networks that we're learning have a bias towards two norms that are small. So it's trying to move the points as little as it has to be able to reconstruct in geometry. So some of these deformations are a little, some of these like displacements are a little bit unphysical. You can kind of fix this away with using some other techniques, but I don't think you should do that to your spatulas. So I'm pretty happy with what we have. Now, going one step further, you can do something we call NDCF, which the previous one was primarily object-centric. This one varies a lot more about contact. So previously, we were just looking at predicting sign distance fields. I also want to be able to predict where the contact is being made with the environment. And so the representation looks very, very similar, but now we're going to train it all in sim. So here's our sort of sponge. We're going to bang it into a bunch of different objects in sim, collect our data, train our model, and show you sort of reconstruction results. So here, that is a partial view that I give my model in sim. Our reconstructions, if you use explicit methods, and here's the ground truth. And what's really nice is that explicit methods really break down quickly, whereas ours is very graceful in this regard. Now you might say, how do you evaluate contact in the real world? It's a fun problem, right? How do you know you've done a good job of estimating contact patches in the real world? If you have good ideas, tell me. This is what we came up with. We basically had the robot grab sponges and we put an acrylic plate in front of it. We had it kind of jam the sponge into the acrylic plate and we put a camera behind it. So the camera is looking at the acrylic plate, seeing the deformation, inferring the contact patch, and we measure the difference between our model's predictions and ground truth measurements from the camera. And so what's really nice is despite this very sort of partial point cloud that you get to perceive, you can still do a pretty great job of 3D reconstruction of the entire object and a pretty reasonable job of the contact patch estimation, despite it being completely visually occluded and this being an ill-posed inverse problem. It doesn't just work on acrylic. Here's a video from earlier. It's basically touching the YCB mug. Again, we can estimate just from this view, what is the object's 3D geometry, what is the contact patch. Doesn't just work on mugs, we can make it work on bowls and whatnot. And so it's pretty powerful. Good. And one last thing that I want to show you is, okay, now that you have these perception capabilities, how do you go from perception capabilities to controls capabilities? And it's kind of fun. What we are going to do here is we're going to bind our contact. We're going to do everything in the contact patch domain. So we're going to write down our controllers as a sequence of contacts made with the environment. And I'm going to force our robot to try to match those contacts in the environment using our models. So here again, the robot's goal is to take the current contact and make it match the future contact. That's literally it. That's the whole objective here. And so we do it in sim and zero-shot transfer to the real world. You're going to see generalization. So the robot has never seen sort of these configurations before. It hasn't seen this dustpan before. And it's able to, again, sim to real zero-shot it. It doesn't just work on dustpans. You can do wiping tasks. You can do random button pushing tasks. It's really cool that it doesn't get confused between the colors. And that's super exciting. So where are we in terms of state of the art? Currently, I would say implicit function representations of deformable objects is essentially a solved problem. Other groups have made a lot of progress on articulated objects. So this is a group from Berkeley with a really cute title, Robot See, Robot Do. There's a group from Dieter Fox at UW. So I say our group and these two groups have really resolved these two problem domains. What's still outstanding is classically deformable objects, wide open, and nobody knows how to do these for very deformable objects, I mean cloth. So these are like wide open problems. It's not even clear whether this is the right kind of representation for cloth. Graph neural networks are a more popular paradigm. Now, just to sort of try to wrap up, I hope that I've convinced you that tactile sensing is cool. I hope I've convinced you that model-based methods are still cool. And sort of since you're all a Control Z crowd, this is kind of a very familiar visual. I've shown you everything kind of highlighted in these orange. Mostly my group is focused on representation learning and perception. We don't do a whole lot on the control side. What I do believe in is that we're in need of causal and feature-rich representation. So what I mean is I want to be able to explain and predict. I want to reason over context, forces, and geometry. Now, if you've been watching the news in robotics recently, you've seen a lot of progress made on large behavior models. This is something that TRI is pushing. You may have seen, this is from Marco Hutter at ETH. This is massive scale reinforcement learning, distillation into the real world. Super cool. And this is from Davide's group. And this is aggressive flying with reinforcement learning. And so these are much more pixels to torque kind of approaches. And so the question, back when I was doing my PhD was, machine learning was becoming hype. Are we going to keep doing first principles methods versus learning methods? And this is no longer really a question. Learning is here to stay. The next big question, at least I think in our field, is do you do raw sensory feedback, so pixels or torques, versus do you do abstract features? This is kind of where the debate currently is. And I would say it's really been inspired by this bitter lessons argument from Rich Sutton, which is saying, will scaling and compute for search and learning just obfuscate the need for human expertise or not? He argues yes. I don't know. What I'm going to argue for is that anyway, planning is search. You're going to need to plan at some point. And having object-centric representations is a key ingredient to planning. And so I think there's a lot of value in continuing to do this research. Our abstract features, so geometry, context, and forces are very useful inductive biases. Think how machine learning, computer vision wasn't really working before CNNs. I think that manipulation and dexterity won't really work before we think about geometry, context, and forces. The future is probably some fusion of these large behavior models and edge planning. And there's a difference between understanding and doing. And with that, thanks to my awesome group. Thank you for listening and questions.
A question for me.
What's up?
So you said the lens feedback. Does it mean again that you have like a contact for sensor or whatsoever additional sensor? How the lens feedback is input? How you create that?
The robots have access to it from the. So basically, each robot has a torque sensor in its wrist.
Okay.
Sorry, a torque sensor at each joint,
Okay.
and from that you can infer wrench of the wrist.
So the intuition though is that have you trained also with that feedback, or you just know you have developed this deformation properties visual, with the visual feedback, and then you combine in the real-time test time with the lens feedback to account for the occlusions.
They're co-trained, so we train on both at the same time. The force gets you about 80% the right way, and then vision kind of cleans it up. Usually it's the other way around, but for these implicit representations, it seems like force is a massive cue.
Yeah, I was thinking in terms of this example with the chain, right? That in order to infer, despite the occlusions, that yes, essentially the chain sits halfway on.
Exactly, it'll be much lighter, right?
Okay.
Yeah, so it has a much
But
bigger
also,
cue.
yeah, how it has deformed. Okay, yeah, thank you. Yeah.
Cool, yes, what's up?
Yeah, in the algorithm where you said you perform the learning in the latent space directly, and that basically lets you, because if you do it there and then you map two different sensor patterns in there.
Yeah.
Could you just go over how you like enforce, make sure the latent space is good? How do you make sure the two, the sensor mappings in the latent space, are actually being sort of enforced to be the same? Yeah, like how do you make the blue and yellow, not together essentially?
Yeah, that's a really good question. It actually took us a large amount of engineering to get that right. So traditional literature in clip models suggests that the larger, so there's the loss itself, which is infra and CE. That's pretty, I would not touch infra and CE too much. The most important factor there is the size of positive negative pair batch sizes. So your batch has one positive negative pair and an n, sorry, one positive pair and negative pairs. And computer vision language models suggest that the bigger that is, the better everything works. For us, that was not the case. It sort of peaked at having 256, like 255 negative pairs, one positive pair. We have peak performance and it dropped off for some reason. It might be because our the scale at which we collect data is much, much smaller. But that is the most important thing to pay attention to. Like, how big is that batch size? If you get that right, the rest is pretty much clip modeling 101.
Oh, and sorry, just one other thing. Those, those are like encoders, right? Are they the same? Is the encoder for the gel sim the exact same one as for the soft bubble sensor?
Thanks for the great talk. I really appreciate the take-home messages at the end. I have a fairly simple question. I think given
Your
all the
questions are
advances-
never fairly simple.
I think given all the like amazing advancements your group has done, what do you think remains before I have a robot at home do my dishes and cook my meals?
I think generality at scale is the biggest problem right now. Some of our techniques are too slow. Some of them don't scale quite as well as we'd hope they would. It's just that the problem is like variety. Sheer variety is like the big problem. So my thinking here is probably where I just was trying to say there's going to be large behavior models like at scale RL. They're going to form the backbone to most behavior. And I think realistically speaking, we're going to do on the fly model learning and fine tuning for sort of downstream applications. And they will be kind of application specific. I'm hoping that is true and I get to do the edge planning part and edge control part. There is a world in which I'm wrong and it's just like end to end. Just throw data at it and it'll be fine. But the big problem is just addressing generality. It's like super hard. And you might say, well, so how do you argue that? My kitchen probably looks quite different from yours. It's going to look different from someone's kitchen from Korea. It's going to look different from someone's kitchen from India. Most of this data is collected in like the Bay Area, right? Like they can collect all the data that they want for weeks and weeks and weeks on end, but it won't match the distribution of real world data very well, even in America, never mind the rest of the world. So there's like serious concerns around sort of generality. So groups are thinking about, are there feature abstractions that will help generalize and so on? And then we hit the bitter lessons argument of like, should you feature engineer at all or not? Or should you just scale up compute and keep throwing things at it? And everyone's betting, right? Literally everyone is betting. TRI and Co and Pi are betting on large behavior models. And other companies are betting on other things, right? It's a big gamble. It's a fun time. Stressful. Yeah.
I'm just wondering how you decided on the soft bubble sensor. And what kind of materials are involved? Is it customizable? Can you change the air pressure? How did you decide on that? Is it what most people are doing these days or?
I can tell you the honest answer, they funded that. And so like it made a lot of sense at the time. And I think we're still excited about them. They're very, very easy to make. So we make them in batches. They're like maybe $20 each. It's like, okay. So the funny story about like where we buy the membrane material from, we get a lot of calls from this college of like, why are you shopping from this vendor? Because they serve other communities that is interesting. But no, they're super easy to make. And I think there was an artifact of the time and the place that we were doing this research. The techniques kind of generalize pretty well to other sensors. And so we just make our own now, gel sims and whatnot, and we're buying digits now and it's just fine. I wouldn't maybe overthink it. They're really great for large objects and force switch interactions, but they're not very good at picking up pens. Like if I drop my pen, I'm doomed. Like the robot will never pick up the pen. So they're not really good for fine manipulation. They're really good for like picking up jugs, picking up dishes, picking up big things.
One more question, then it'll be 4:30.
So, you showed that video in which the robot was picking up some balls and it had different configurations for tools it had slightly different scenarios or the the tool was in a different position. So I was wondering how flexible is the algorithm to accommodate different tools? For example, you know, pick up tray that has a different shape or something like that. And if there's not much flexibility, what's the barrier for that?
Yeah, it is pretty good with in-class generalization. So if I give you things that kind of look like spatulas, it'll be very good. We tend to find that they work best when you train per class. So there'll be a class for spatulas, there'll be a class for forks, forks and spatulas might be close enough, but you need to do classes of objects. And the reason why is that the topology of the optimization landscape for learning those models actually has a ton of local minima. And the more complicated the set of geometries you want to generalize over and all the deformations they can do, it gets way worse really quickly. So for like high quality, high fidelity reconstruction, probably per class, if the tasks are not that sensitive and you're okay with like artifacts showing up in your reconstructions, I'd say you can get away with like larger classes. But if you want like really high fidelity stuff, which is what graphics people do, graphics people train one model per object. And there's like super high quality reconstructions. There's a bunch of other things. So like we use ReLU activations. They have been shown to have low bandwidth representations. They kind of basically trim off high resolution features, but they have really easy optimization landscapes. Graphics people are like advocates for sine waves. They make really high quality, really sharp reconstructions, but they have awful optimization properties. And so there's a bunch of like knobs you have access to kind of like tune to be able to have like better generality across larger distributions of objects at the cost of resolution. And it'll depend on the object.
Thank you very much. Very interesting presentation.
Thank you.
Favorite speaker again and.
We need a white.
Yeah, he talked to a future students.
Thank you.
Jobs. Oh, I see, actually, she had all. It wasn't the issue, yeah, the issue.
Nuclear power plants. Oh my gosh.
So that's what I'm working on. So I kind of like the video you put at the beginning.
Wally?
I
Yeah.
don't know if you can share with me or something.
Sure. It's I just found it on YouTube.
YouTube.
Yeah, it's in the movie Wally. It's Wall dash.
Wall dash E.
Yeah, it's a really famous Pixar movie.
Oh, I see.
Yeah,
Thank you.
it's a super famous Pixar movie. So, and I just took a clip from YouTube. It's an awesome movie.
And, you know, trying to finish up.
Thank you.
Need to revise it.
I see.
About I want to know if you have, for example, a convention of automatic robots.
You do.
That's a really how many robots
Yes.
yeah, but it would be cool to explore. You've worked on multi-robot.
Yes, but that's, by the way, I have to introduce a social professional beginning. Nice to meet you. She's my wife. So we're doing with a dual career. And she's looking into robotics.
Got it.
I
Yeah.
also thinking about your field.
So he's.
The population, population next.
It's a very exciting area.
You guys
Get through their system.
Yeah.
He's trying. Those are.
No worries. Yeah, we talked about actually talked to Kira, so.
Yeah, they're not the right people.
Yeah, no, the right people.
They're like, great, I'm getting like.
I know. Well, they are my colleagues, so.